In problem 1, we're going to use the limit process to find the derivative of 3x minus x squared. So we're going to find the limit as delta x approaches 0 of 3 times x plus delta x minus x plus delta x squared minus f of x, which is 3x minus x squared, all over delta x, and simplifying that, we'll get 3x plus 3 delta x minus x squared plus 2x delta x minus delta x squared minus 3x plus x squared all over delta x. And so our 3x's should cancel. And since the negative distributes, our x squareds will cancel. So we're going to be left with 3 delta x minus 2x delta x plus delta x squared all over delta x. And we can cancel out a delta x. So we'll have 3 minus 2x plus delta x. And since we're taking the limit of that as delta x approaches 0, we'll know that f prime of x equals 3 minus 2x. So now we want to find f prime of 1, so we just take 1 and plug it in for x, and f prime of 1 equals 1. For number 2, we want to differentiate y equals 3x over x squared plus 1. Since we have two terms that are in the denominator, we have to use the quotient rule. So the quotient rule is the derivative of the top, which we'll call f, times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. So the derivative will be the derivative of the top, which is 3, times the bottom, x squared plus 1, minus the derivative of the bottom, which is 2x, times the top, all over the bottom squared. And we'll just leave that as x squared plus 1 squared. So since we have no negative exponents, we don't have to simplify that anymore, unless we want to distribute the 3. And that will become 6x squared. So then our final answer can be negative 3x squared plus 3 over x squared plus 1 squared. In problem 3, to find dy dx, which is just the derivative of y, we can do two things. We could either use the product rule, or we can distribute the square root of x, which is really x to the 1/2, and differentiate each term. So I think it would be easier to distribute the x to the 1/2. So we get that y equals 3x, and it would be 1 plus 1/2, which would be 3/2, minus x to the 1/2. And now we're ready to find the derivative. So using the power rule, we would get 9/2 x to the 1/2 minus 1/2 x to the negative 1/2. And to leave the answer with no negative exponents, we should write the final answer as 9/2 square root x minus 1 over 2 root x. For number 4, since we have sine cubed of 4x, we're going to rewrite that as the sine of 4x cubed. And now we can see that we have to chain rule. Actually, in this one, we're going to need to triple chain rule since we have 3 functions going on. We have the cube on the outside, we have the sine on the inside, and then we have the 4x on the inside of the sine. So, to chain rule, we're first going to take the 3 out in front using the power rule, and then the exponent goes down by 1. Now we need to take the derivative of sine of 4x, which is cosine of 4x. And now we need to go even further and take the derivative of 4x, because that is the innermost function, and that derivative is 4. So our final answer will be 12 times sine squared 4x times the cosine of 4x. In problem 5, we want to find the second derivative of y equals x plus 2 over x minus 3. So whenever you have these 2's right here, that means that you're going to find the second derivative. So first we will find the first derivative, and we need to use the quotient rule. So we're going to do the derivative of the top, which is just 1, times the bottom, x minus 3, minus the derivative of the bottom, which again is just 1, times the top, all over the bottom squared. So that will simplify into, the x's will cancel out, and that will just be negative 5 over x minus 3 squared. Now we need to take the derivative again. However, I think to take the derivative again, it would, instead of doing the quotient rule, it would be easier to rewrite it as negative 5 times x minus 3 to the negative second and use the chain rule to take the derivative. So we'll get a positive 10 times x minus 3, and we'll subtract 1 from the exponent, so that will be to the negative third. And we still need to take the derivative of the inside, but that will just be 1. So it's really just multiplied by 1. So then our final answer will be 10 over x minus 3 cubed. For number 6, we want to find the derivative of x squared plus y squared equals 2xy. And since we have x's and y's on the same side and on the same side here, and there's no real easy way to isolate y, we are going to use implicit differentiation. So that means that every time I take the derivative of y with respect to x, I need to add in a y prime. So the derivative of x squared is 2x. The derivative of y squared is 2y. But since we're taking the derivative with respect to x, we need to add in a y prime. And when I take the derivative of the right side, I'm going to need to use the product rule because I have 2xy. So to do the product rule, I'm going to do the derivative of the first function, which is 2x, so just 2, times the second, plus the derivative of the second, so that'll be y prime times the first. And now I want to isolate y prime. So I'm going to subtract the 2y over to the left side and subtract the 2y y prime. Then I'm going to factor out the y prime. Then we can divide by 2x minus 2y. And we just end up with a 1. So 1 will equal y prime. For number 7, we also need to use differentiation to find dy dx. So take the derivative of x, we get 1. And to take the derivative of the tangent of x plus y, we're going to need to use the chain rule since we have an outside function and an inside function. So the derivative of tangent is secant squared. So we're going to have the secant squared of x plus y, but we still need to multiply that by the derivative of the inside. So the derivative of the inside would just be 1 plus y prime. So we still need to get y prime by itself, so we're going to divide by secant squared of x plus y, and that gives us 1 plus y prime, and then we'll just subtract the 1. So since we were asked to find dy dx, we can say that dy dx equals 1 over secant squared of x plus y minus 1. For number 8, we want to differentiate cosecant squared theta, which I'm going to rewrite as cosecant theta quantity squared, which means we'll have to use the chain rule, plus cotangent theta quantity squared. So first we need to do the derivative of the outside function, which is the squared. So we'll get 2 times the cosecant of theta raised to the first, and then we need to multiply that by the derivative of cosecant theta, which is negative cotangent theta cosecant theta. And now we need to do the same thing for the next term. So we'll have 2 cotangent theta raised to the first power. And then we'll take the derivative of cotangent theta, which is negative cosecant squared theta. So then we'll get a negative 2 cotangent theta cosecant squared theta minus 2 cotangent theta negative, we pulled the negative out in front, cosecant squared theta, which simplifies to negative 4 cotangent theta cosecant squared theta. Number 9 is more chain rule. So first I'm going to rewrite it as the secant of t to the 1/2. And this time the 1/2 is only affecting the t. So first we want to take the derivative of the outside function, which is secant. And we're going to get the secant of t to the 1/2, since that's the inside function, times the tangent of t to the 1/2. But now we still need to multiply that by the derivative of the inside function, which would be 1/2 t to the negative 1/2. So then our final answer will be the secant, say this is s prime of t. It will be the secant of the square root of t times the tangent of the square root of t all over 2 square root t. Number 10, we're given the position function of a particle. We know that it moves along the curve by y equals the square root of x cubed plus 1, and we want to find the acceleration of this particle at 2 seconds. So we know that acceleration is the second derivative of the position function. So first we need to find the second derivative of y. So first I'm going to rewrite y as x cubed plus 1 to the 1/2. And if I take the first derivative of that, I'm going to need to use the chain rule. So I'll have y prime equals 1/2 times x cubed plus 1 to the negative 1/2 times 3x squared. So simplifying that a little bit, we'll have 3/2 x squared times x cubed plus 1 to the negative 1/2. So that's the first derivative, but now we need to find the second derivative. So to get the second derivative, since I have two functions being multiplied together, I'm going to have to use the product rule. So to find the second derivative, we need to do the derivative of the first function, which is 3/2 x squared, which will just become 3x times the first plus the derivative of the first, which again we're going to have to use the chain rule to take the derivative of that. So I'll get a negative 1/2 x cubed plus 1 to the negative 3/2, but I still need to multiply that by the derivative of the inside, which is 3x squared. And I still need to multiply that by the first function, which was 3/2 x squared. So let's do some simplifying before we plug a 2 in to make our lives a little bit easier. So first I'm going to factor out the smallest exponent, which is x cubed plus 1 to the negative 3/2. So we'll take that out, and then we'll write down what we have left over. So we have a 3x times, and if I take negative 1/2 and subtract a negative 3/2, it's like adding 3/2 to it, which will just make it a 1. And then I'll have a negative 1/2 left over times a 3x squared times a 3/2 x squared. So that would be a negative 9/4 x to the 4th. And if we like, we can simplify one step further, because I can distribute that 3x to get 3x to the 4th. And plus 3x minus 9/4 x to the 4th, which will give me 3/4 x to the 4th plus 3x. And if I want to factor out the 1/4, I could do that. Make it even a little bit prettier. So it'll be 1/4 times x cubed plus 1 to the negative 3/2 times, on the inside, a 3x to the 4th plus a 12x. So now we're finally ready to plug in a 2 to see what the acceleration is at 2. So y double prime of 2 is going to equal 1/4 of 2 cubed plus 1, which is 9, to the negative 3/2 times 2 to the 4th is 16, and 16 times 3 would be, what, 48? And then 2 times 12 is 24. So if we do 9 to the negative 3 halves, it would be the square root of 9, which is 3. Raised to the third is 27, but since it's a negative exponent, it will be 1 over 27. And then that is still times 48 plus 24, which is 62. Nope, 72. So 4 goes into 72. I think, what is it? 18 times, so we get 18 over 27, which would be 2/3. So all that work for 2/3, our final answer. For number 11, we want to find an equation for the tangent line at x equals 1. So first thing we want to do is find the slope, so we have to take the derivative. So f prime of x will equal negative 4x plus 2. And now we want to find the slope of the tangent line at 1. So we'll plug in a 1. And if we plug in a 1, we get a negative 2. So I want to use point slope form, except I only know x equals 1. I don't know the other point. So first we have to find f of 1. So we know what our y value is, so we can then put it into point slope form. So that would be negative 2 plus 2 plus 3. So we know we have our point at 1, 3. So the equation of our tangent line would be y minus 3 equals negative 2 times x minus 1. And we can just leave our equation in point slope form. Now we want to find the points on the graph for the function f of x equals x cubed minus 2, where the slope is 3. So since slope is the same as derivative, we want to first take the derivative, which is 3x squared. And then we're going to set that equal to 3. And we get that x can equal plus or minus 1. So there'll be 2 points on the graph that we know of that where the slope will be 3. So to find the y values, I can just plug them in. So f of 1 will be a negative 1. And f of negative 1 will be a negative 3. So my 2 points are 1, negative 1, and negative 1, negative 3. For number 13, we want to find the instantaneous rate of change of w with respect to z. So when we see the words instantaneous rate of change, that is the same as the derivative. So all we want to do here is take the derivative of w with respect to z, which will just be w prime. So we're just taking the derivative like normal. So first I'm going to rewrite w as z to the negative 1 plus 1/2 z. And that should be a little bit easier to take the derivative of. So w prime will equal negative z to the negative 2 plus 1/2. And then just to rewrite it with no negative exponents, we'll have negative 1 over z squared plus 1/2. In number 14, we want to find the velocity of the object when t equals 2. And we want to remember that velocity, the equation for velocity is the first derivative of the position function. So first we want to find the derivative of s of t, which will be 6t minus 2. And now we can find v of 2 by just plugging a 2 in. And that will be 12 minus 2, so 10. And then we want to make sure we write down the units, which is meters per second. So now I realize that I forgot to write down the units for the for the acceleration in problem 10. So let's go back to problem 10 and we'll write down the acceleration. The video is getting kind of messed up here, but it would be units per second squared, since they didn't give us what the distance was measured in. Alright, for our last problem on this page, 15, we want to find the derivative of the following. And so if we want to find the derivative of f of x times g of x, that is just the product rule. So the derivative would be f prime of x times g of x plus f of x times g prime of x. And for part B, we have f of g of x, and that would be the chain rule. So we do f prime of g of x times g prime of x. For part C, we have 2x to the fourth times g of x, and that would be another product rule since we have two functions multiplied together. So that would be 8x cubed, derivative of the first times the second, plus the derivative, plus the first times the derivative of the second. And then finally we have D, which is f of x over g of x, and that would be the quotient rule. So we have f prime of x times g of x minus g prime of x, f of x, all over g of x squared. For number 16, we want to find at least one coordinate of the points where the tangent line to the curve is horizontal or vertical. So we will have a horizontal tangent line whenever the derivative is 0. So first let's find the derivative of our function, and we'll have to use implicit differentiation. So we'll have 3y squared y prime plus 2y y prime minus 5y prime minus 2x equals 0. And so now I want to isolate y prime. So I'm going to move the 2x to the other side and divide by the remaining terms. So I'll have 2x all over 3y squared plus 2y minus 5. And so now I know that the derivative will equal 0 whenever the numerator equals 0, which will happen at x equals 0. So now to find out what y equals when x equals 0, I just have to plug a 0 in for x and solve for y. So I will get y cubed plus y squared minus 5y equals a negative 4, or I'll add 4 to the other side. Actually, it says find one coordinate of the point. So we found the x coordinate, so we're good. We don't even have to solve for the y coordinate. So we are not even going to bother with that. Oh, it won't let me erase. Oh well. Alright, so x equals 0 is our first answer. Now we have to find where we're going to have a vertical tangent line. And that will occur when the derivative is undefined or when the denominator equals 0. So we'll set the denominator equal to 0, and hopefully it is factorable. I think if I put a 1 here, a negative 1, and a positive 5, that will work. So at y equals negative 5/3 and at positive 1, I will have a vertical tangent line. For problem 17, we want to find the derivatives of the absolute value functions. So first we take the derivative of the inside, which in this case will be 2, and then we put the function in the numerator and then the absolute value of the function in the denominator. And we'll do the same thing for part B. We'll take the derivative of the inside, which is 2x, and then put the function in the numerator and then the absolute value of the function in the denominator. For problems 1 through 11, we just have more practice with derivatives. So I'm going to need to use the product rule for number 1. So I'll do the derivative of the first, which is 5x to the fourth, times the second, plus the first, times the derivative of the second. So it looks like choice E is my answer. For number 2, I need to use the quotient rule. So I'm going to do the derivative of the top, which is a -1, times the bottom, minus the top. Well, we'll do the derivative of the bottom first, times the top, all over the bottom squared. So let's simplify the top so we can get it to look like one of our multiple choice choices. So we'll get -3x minus 1 minus 6 plus 3x. So that will just give us a -7 on the top and a 3x plus 1 squared on the bottom. So that would be choice A. For 3, I'm going to first rewrite this as 3 minus 2x to the 1/2. And then when I take the derivative of that function, I'm going to have to use the chain rule. So I get 1/2 times 3 minus 2x to the -1/2. But I still need to multiply by the derivative of the inside, which will be a -2. So I am going, the 1/2 and the -2 will just become a -1. And then I can have the square root of 3 minus 2x brought to the bottom. So that will be choice B. For problem 4, I'm going to rewrite this function so it's a little easier to take the derivative of, and then I won't have to use the chain rule, or I'm sorry, the quotient rule. And instead I'm going to use the chain rule. So the derivative will be a -6 times 5x plus 1 to the -4th. But I still have to take the derivative of the inside, which will be times 5. So I'll get a -30, and then the 5x plus 1 to the -4th can get sent to the bottom. So, oh, actually, we just have the answer with the negative exponent right there. So it would be choice B. Number 5, I don't need to rewrite anything, so I'll just have that the derivative is a 3 times 2/3, which would be 2. So 2x to the -1/3. And then 4 times 1/2 is just minus 2x to the -1/2. And then those negative exponents can get set to the, oh, no, we have the answer right here, choice E. For problem 6, I'm going to rewrite it as 2x to the 1/2 minus 1/2 x to the -1/2 before I take the derivative. So now I'm ready. So 2 times 1/2 will just be 1. So I'll get x to the -1/2. And 1/2 times a -1/2 would be a positive 1/4. Now it will become x to the -3/2. So unfortunately none of my answers, or my answer doesn't look like any, oh it does, it looks like B. And this one's actually a little bit tricky because if I rewrote it, it would also be the same as choice D. So this one I'm not going to give you one on the test where you could have 2 choices, just pointing that out to you, that if I say write it without negative exponents, it would have to look more like D, or the way I have it written. For number 7, I'm going to rewrite it before I take the derivative. And when I do the derivative, I'm going to have to use the chain rule. So we have 1/2 times x squared plus 2x minus 1, and that's to the negative 1/2. But I still need to multiply by the derivative of the inside, which is going to be 2x plus 2. So 2x plus 2 can stay in the numerator. And then the 2 and the square root of x squared plus 2x plus 1 can go in the denominator. However, the 2 on the bottom will cancel with the 2 2's up top. So since it's kind of tricky, since it's not negative, it is very close. Oh, that's to the 3/2. So this one would be none of these answers. For number 8, we're going to have to use the the quotient rule. So we're going to do the derivative of the top, which is 1 times the bottom. So that'll be 1 minus x squared to the 1/2 minus the top, and then times the derivative of the bottom. So that one we're going to have to chain rule. So we have 1/2 1/2 times 1 minus x squared to the negative 1/2. And then the derivative of the inside will be a negative 2x. And that's all over the bottom squared. So that will just be a regular 1 minus x squared. So we're going to have to work on simplifying this a little bit to get it to look like one of our choices below. So, let's see here. Looks like we can factor out a 1 minus x squared to the negative 1/2. And then we'll see what we have left in the inside. So if I factor that out, that will make the first one a 1 minus x squared to the first power, since 1/2 minus a negative 1 would be 1. And then we'll have the negative 2x and the negative x will become a positive. And the 1/2 and the 2 will cancel, so we'll just be left with an x squared. And the 1 minus x squared is factored out. So we'll just end up with a 1 right there, and that's over 1 minus x squared. And so then the 1 minus x squared to the negative 1/2 will be dropped down to the bottom, which will make it a 1 over 1 minus x squared to the 3/2. So again, kind of tricky. The answer is, again, none of these. For number 9, again, we need to use the quotient rule, but this time it should be a little bit easier for us. So we'll do the derivative of the top, which is 2x times the bottom, minus the derivative of the bottom, which will be a negative 2x. We'll turn that to a positive, times the top, all over the bottom squared. And then let's simplify top. So we'll get 2x minus 2x cubed plus 2x plus 2x cubed. So it looks like we'll just be left with a 4x on the top and a 1 minus x squared squared on the bottom. So that will be choice B. For number 10, we need to do some implicit differentiation, and also we're going to have to product rule this middle term right here. So we'll start off with a 6x minus, and then we'll have to product rule. So I'm going to put this in parentheses. the derivative of the first, which is 2, times the second, plus the derivative of the second, which is y prime, times the first, so 2xy prime. And then that'll be plus 10y y prime, and that will all equal 0. So now we need to get y prime by itself. So I'm going to leave the 2x y prime plus 10y y prime on the left side. And I'm going to add the 2y over and subtract the 6x. And then I'll have y prime equals 2y minus 6x all over 2x plus 10y. And then I can divide everybody by 2. So that'll be y minus 3x over x plus 5. Oops, so I missed a y up there. Copy problem. So that'll be a y down here. So then that'll be an x plus 5y on the bottom. Oh, and I see another mistake. This should be a negative 2xy y prime. Distribute the negative. So that means that this x is negative. So that x is negative. There we go. So then we should have choice B. For problem 11, we want to find the second derivative and then plug in a 4. So we're going to rewrite it as 16x to the 1/2. So then the first derivative will be 8x to the negative 1/2. And then our second derivative will be negative 4x to the negative 3/2. So then if I plug a 4 in, well, let's rewrite it as negative 4 over x to the 3/2. So if I plug in a 4, I will get negative 4 over the square root of 4 cubed. And the square root of 4 is 2. 2 cubed is 8. So that will be a negative 1/2, which is choice E. For number 12, we're given the graph of f of x, and we want to sketch the graph of dy dx, which is the derivative. So when we're sketching the derivative, we want to take a look at the slopes and graph the slopes. So if I take a look at this portion of my graph, the slope is definitely 0. So I'm going to have a line at 0 to show that all my slopes remains a function. I'm going to have a So now I'm going to take a look at this portion of my graph, and it looks like it's a constant slope. It looks like we go up 1, 2, 3, 4, and then over 1, 2, 3, 4. So I have a slope of 1. So I'm going to draw a horizontal line at 1. It's a little too high. There we go, to show that I have a slope of 1 for all those points. So now we have another constant slope in this area, and it looks like this is down 1, 2, 3, 4, 5, 6, and then over 1, 2, 3. So we have a slope of negative 2. So I'm going to draw that I have a slope at negative 2 for all of these points. And remember, our slope is undefined at a cusp or a sharp turn like we have right here and right here. So that's why we did some little undefined points. For problems 15, 16, and 17, we want to use the chart to help us find a prime of 3, and we're given that a is f plus 2g. So we want to know that if we want to take the derivative of something like f plus 2g, it's as simple as taking the derivative of f and then plus 2 times the derivative of g. So if we want to find a prime of 3, we just want to know what f prime of 3 plus 2 times g prime of 3 is. So it looks like that f prime of 3 is 4, just by looking at the chart. Here's 3, and here's f prime. And g prime of 3 is negative 1. So that'll be 2 times negative 1. So my answer will be B, 2. B is f times g. So if we want to know B prime of 2 and the derivative of b, we're going to have to use the product rule. So b prime is going to equal f prime times g plus f times g prime. So if we want to know b prime of 2, we're going to need to know what f prime of 2 is times g of 2 plus f of 2 times g prime of 2. So f prime of 2 would be 3. G of 2, regular g of 2 would be 1. F of 2 is 5. And g prime of 2 is negative 2. So it looks like our answer will be negative 7. If d is 1 over g, or g to the negative 1, then d prime will be negative g to the negative 2 times g prime, since we need to chain rule it. So, rewriting that would be negative 1 over g squared times g prime. So, d prime of 1 will be negative 1 over g of 1 squared times g prime of 1. And g of 1 is 3, so that'll be negative 1 over 3 squared times g prime of 1, which is negative 3. So that will be 3 over 9, which will be a positive 1/3. If k is f divided by g, then to find k prime, we need to do the quotient rule, which would be f prime g minus g prime f over g squared. So we'll need to find f prime of 0 times g of 0 minus g prime of 0 times f of 0 over g of 0 squared. We're going to have to take a look back at the table to get all of those values. So that will be 1 times 5 minus negative 4 times 2 all over 5 squared. So we'll have 5 plus 8, which is 13 over 25. So that will be choice C. If m is f of g of x, then to find m prime, we need to do the chain rule. So we'll have f prime of g of x times g prime of x. And we want to do m prime of 1, so that'll be f prime of g of 1 times g prime of 1. And we'll have to go back to the table to look at these values. G of 1 is 3, so we'll have to find f prime of 3. And g prime of 1 is negative 3. And f prime of 3 is 4. So we have 4 times negative 3, which is negative 12. So we have choice A. For number 20, we know that p of x is f of x cubed. So if we want to find p prime of 1, we'll again have to do the chain rule. So we're going to have f prime of x cubed times 3x squared. And in this case, x is 1. So we want to know what f prime of 1 cubed is, which is just 1, times 3 times 1 squared. So f prime of 1 is 2. So we have 2 times 3, so 6. 21 asks where can we not differentiate functions? And we can't differentiate functions at any sharp turns. So that would be at the vertex of an absolute value function, for example, right here. We cannot differentiate functions at cusps. So that would be if a function does something like that. And we cannot differentiate functions where they're not continuous. So if there's any points of discontinuity, it is not differentiable at that point. So for 22, we're given the derivative and we want to sketch the original function. So if we notice some things, we notice that the derivative is undefined at this particular x value. So there needs to be either a cusp or a sharp turn at that point, or not continuous. We also see that this means that we have a slope of, I don't know, we can guess it's about -1 for all these x values right here because it's constant. And then for all these x values, it looks like maybe we have a slope at 2 since it's a little higher. So if I'm going to draw the original graph, okay, I have a slope at -1, so it looks kind of like that. And then I'm going to have a sharp turn, and then my slope will be maybe a little bit steeper on this side since the derivative is up a little bit higher. So we kind of have like a skewed absolute value graph. For 23, we're given the graph of f of x, and we want to sketch the graph of the derivative or the graph of the slopes. So for this first portion, we have a slope of 0. So I'm going to graph 0. And then we have a sharp term, so I'm going to make that undefined. Here, I would guess that we have a constant slope at, I don't know, maybe about -1. So I'm going to have a constant derivative at -1. And then it looks like we have another undefined derivative since we have a sharp turn. And then I'm going to assume that this is about a slope of +1. So I'm going to graph a constant slope up at +1. And then in this region, our slope is changing. And it looks like our slope starts off pretty negative, and then it goes towards 0, and then our slope becomes positive. So I'm going to have my slope start negative, and then it should cross the x-axis right here, because that's where it looks like we have a horizontal tangent line. And then my slope becomes more positive. So now in this region, looks like my slopes are getting very, very, very positive, and then they're going to head back towards 0 again and get less and less positive. So I should have another x-intercept at about this point. So it gets more and more positive, and then it's got to turn around. Maybe I need to draw this little, it won't erase. Oh well. More and more and more positive, and it turns around and starts going back to 0. And then it looks like my slopes stay pretty negative. So now we'll kind of go negative. And that would be an acceptable graph of the derivative. So for our last problem, we want to write the equations of the tangent and normal lines to f of x equals 3 plus tan x over sine x when x equals pi over 4. So to write the equation of the tangent line, we first need to find the slope and the derivative at the point of x equals pi over 4. So to find the derivative, I'm going to have to do the quotient rule. So we'll do the derivative of the top, which will just be secant squared x times the bottom minus the derivative of the bottom, which is cosine x, times the top, all over the bottom squared. And now let's plug in pi over 4 to find the slope of the tangent line. So remember, secant is the same as 1 over cosine, so I'm going to change that to 1 over cosine squared x. Well, let's just plug in pi over 4. So 1 over the cosine of pi over 4 squared times the sine of pi over 4 minus the cosine of pi over 4 times 3 plus the tangent of pi over 4 all over the sine of pi over 4 squared. So now we want to remember that the cosine and the sine of pi over 4 is root 2 over 2. So whenever you take root 2 over 2 and you square it, you get 2 over 4, which is 1/2. So we have 1 over 1/2, which will really become a 2, times root 2 over 2 minus root 2 over 2, and the tangent of pi over 4 is 1, so that will become a 4, all over root 2 over 2 squared, which is another 1/2. So then we'll get 2, so this is just a 2, so that will just be a root 2 minus a 2 root 2 divided by 1/2, so that's really times a 2. So we'll get 2 root 2 minus 4 root 2, which is a negative 2 root 2. So that is the slope of our tangent line. So now we need to put this into point slope form, which means, though, first I have to plug a pi over 4 into my original equation. So we're plugging a pi over 4 in for x to see what our y value is. So that would be a 4 over a root 2 over 2. And if we multiply it by the reciprocal, that would become an 8 over a root 2. So my point is pi over 4, comma 8 over root 2. So then the equation of my tangent line would be y minus 8 over root 2 equals a negative 2 root 2 times x minus pi over 4. And then for our normal line, all we do is do the perpendicular slope. So we'll just change the sign and flip it over. So the normal line will be y minus 8 over root 2 equals positive 1 over 2 root 2 times x minus pi over 4.